Breaking news from the edge of our solar system reveals that 3I Atlas is no longer behaving like a simple comet. Days ago, astronomers watched as this interstellar visitor crossed within 2 astronomical units of the Sun and began brightening far beyond predictions. Its atmosphere has swollen to half the diameter of our star, its glow has shifted to an unsettling green, and most bizarrely, it's developed a tail pointing directly toward the Sun, something that should be impossible. As it races toward Mars at breakneck speed, researchers admit they can't explain what they're seeing. The countdown to perihelion has begun, and with every passing hour, this alien wanderer looks less like a comet and more like a cosmic riddle demanding answers. Stay until the end of tonight's exploration to learn what this breaking story means for everything we thought we knew and what happens when alien chemistry finally awakens. The numbers don't lie, even when they defy explanation. In mid-September of 2025, astronomers monitoring 3I Atlas noticed something unsettling in their data. Brightness measurements began climbing above predicted curves, rising from the expected magnitude of 15 or 16 to a startling 12 to 14. For those unfamiliar with the inverse logic of astronomical magnitudes, this represents a dramatic shift. Magnitude numbers run in reverse. The lower the number, the brighter the object. A drop of just 2 magnitudes means the object is now producing 6 times more light than predicted. But this wasn't a gradual change, this was acceleration. The Comet Observation Database, known as COBS to those who track these celestial wanderers, began showing data points that climbed steadily above the standard upward slope expected for a warming comet. Earth's sky tracking confirmed the trend. 3I Atlas was outshining every model astronomers had constructed for its journey sunward. The critical moment came as the object moved inside approximately 2 astronomical units of the Sun in early to mid-September. For context, 1 astronomical unit is the distance from Earth to our star, roughly 93 million miles. At $2, 3I Atlas was still twice as far from the Sun as we are. Yet something fundamental changed. The brightness acceleration wasn't just unexpected, it was alarming in its intensity. What could cause such a dramatic surge in luminosity? The most likely explanation involves volatile ices, frozen carbon dioxide, water, and exotic compounds locked within the nucleus. Since the object's formation around another star, as solar radiation intensifies, these materials don't just melt. They explosively transition from solid to gas, carrying dust and debris in expanding clouds that reflect sunlight back toward Earth. But here's what should concern us. Rapid brightening events often signal instability. Comets experiencing sudden outgassing can fragment, creating multiple objects or spectacular debris clouds. They can also exhaust their volatile reserves quickly, leading to equally rapid dimming. The fact that 3I Atlas is brightening faster than models predict suggests we're witnessing processes that astronomers don't fully understand. This isn't cause for planetary panic, however. NASA has confirmed that 3I Atlas maintains a safe distance, never approaching closer than 1.8 astronomical units to Earth, nearly twice the distance to our Sun. The alarm isn't about collision, it's about comprehension. We may be watching an interstellar time capsule undergo fundamental changes in real time as it barrels toward the inner solar system. Consider the implications. This object formed in the debris disk around another star perhaps hundreds of light-years away. It condensed from materials that never felt our Sun's warmth, never experienced the specific conditions that shaped the bodies native to our cosmic neighborhood. Yet now, for the first time in its existence, it's encountering the intense radiation environment of our inner solar system. The brightness surge could represent the awakening of chemistry that has remained dormant for millions or billions of years. Exotic ices, stable in the frigid depths of interstellar space, might now be sublimating for the first time since the object's birth. We're potentially witnessing the unveiling of chemical signatures from another star system, preserved in pristine condition across the galaxy. The timing creates additional urgency. 3I Atlas is approaching a series of critical dates that will determine what astronomers can learn from this unprecedented visitor. October 3 marks its closest approach to Mars, a mere 30 million kilometers, close enough for spacecraft orbiting the red planet to potentially observe details invisible from Earth. By late October, specifically October 29 to 30, the comet reaches perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Here's where the story takes a troubling turn for Earth-based observers. As 3I Atlas nears its date with our star, its position in our sky moves dangerously close to the Sun's overwhelming glare. From early October through early November, the comet enters what astronomers call superior conjunction, a period when the Sun's brightness makes observation nearly impossible from Earth's surface. This means the peak activity of our interstellar visitor, the moment when solar heating reaches its maximum intensity and the comet's true nature might be revealed, will occur largely hidden from our view. We'll be forced to rely on the mechanical eyes of spacecraft positioned throughout the solar system, particularly those orbiting Mars, to witness what could be the most spectacular display of interstellar chemistry in human history. The brightening trend suggests 3I Atlas won't go quietly through perihelion. Current observations hint at an object energized by its encounter with our Sun, possibly building toward outburst events that could illuminate previously invisible details of its structure and composition. But will these revelations occur during the weeks when Earth's telescopes are blinded by solar glare? The data emerging from September's observations paints a picture of an object in transition. The measured brightness points trending above predicted curves suggest that 3I Atlas is becoming something different from what it was during its long journey through interstellar space. The question is whether this transformation represents normal comet behavior in an exotic object or something entirely unprecedented in our experience with visitors from other star systems. In the coming minutes, we'll explore why this object's coma extends farther than should be possible, why its tail points toward the Sun instead of away from it, and how its recent shift to an eerie green glow might signal chemical processes never before observed in an interstellar visitor. The mysteries are multiplying as quickly as the brightness measurements are climbing. But first, we need to understand what we're dealing with because 3I Atlas isn't just any comet. It's only the third confirmed visitor from another star system, and its behavior is already proving that each interstellar object carries its own set of rules. The story of 3I Atlas begins on a mountaintop in Chile, where robotic eyes scan the night sky with a mechanical precision that puts human observers to shame. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected a faint smudge of light moving against the background stars. Initially catalogued as just another minor body, this unremarkable observation would soon rewrite our understanding of interstellar visitors. What makes an object interstellar isn't simply its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally bound to our Sun's orbit. 3I Atlas follows what astronomers call a hyperbolic trajectory, a path so energetic that once it completes its swing around our star, it will continue outward forever, never to return. The orbital mathematics are unforgiving in their precision. This object carries too much velocity to be captured by our Sun's gravity. The 3I designation tells its own story. The I stands for interstellar, while the number 3 indicates this is only the third such object confirmed in human history. Its predecessors, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, each surprised astronomers with unique characteristics that defied easy categorization. Now, 3I Atlas continues this pattern of interstellar unpredictability. The discovery process reveals just how difficult these objects are to catch. ATLAS operates from the Rio Ardo Observatory in Chile's Atacama Desert, part of a global network designed to spot potentially hazardous asteroids approaching Earth. The system captures multiple images of the same sky region over short time periods, then uses computer algorithms to identify anything that moves against the stellar background. On that July night, 3I Atlas appeared as little more than a faint streak barely distinguishable from the thousands of asteroids, comets, and space debris that populate our inner solar system. But recovery images, earlier photographs that show the object before its official discovery, revealed that 3I Atlas had been lurking in astronomical databases for weeks before anyone recognized its significance. This delayed recognition is common with interstellar objects, which often appear asteroidal in early observations before developing the fuzzy comas and tails that mark them as comet-like bodies. The initial assessment showed a faint coma surrounding the central nucleus, immediately suggesting that 3I Atlas was more than just a rocky asteroid. Comets develop these fuzzy atmospheres when solar heating causes ices to sublimate, creating expanding shells of gas and dust. The presence of a coma so far from the Sun, 3I Atlas was still beyond 3 astronomical units when discovered, indicated that this object contained volatile materials capable of outgassing even in the cold outer reaches of our solar system. As news of the discovery spread through the astronomical community, larger telescopes began turning toward this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their own observations. These follow-up studies revealed an object far more complex than its initial discovery images had suggested. Size estimates for 3I Atlas remain frustratingly uncertain, a common problem when studying objects too distant and faint for direct measurement. Hubble's August update narrowed the possibilities to a nucleus somewhere between 0.32 and 5.6 kilometers in diameter, a range that reflects the difficulty of separating the solid nucleus from its surrounding coma. The size uncertainty matters because it affects calculations of the object's mass, density, and structural stability as it approaches the Sun's intense heating. Speed calculations paint a clearer picture of this object's extraordinary nature. Currently racing through space at approximately 130,000 miles per hour, roughly 58 kilometers per second, 3I Atlas moves at velocities that dwarf anything naturally occurring in our solar system. For comparison, Earth orbits the Sun at a sedate 30 kilometers per second. The comet's speed will continue increasing as solar gravity accelerates it toward perihelion, potentially reaching 68 kilometers per second, or more than 150,000 miles per hour. These velocities underscore the alien nature of our visitor. No object born in our solar system could naturally achieve such speeds without assistance from gravitational slingshot maneuvers around massive planets. 3I Atlas carries the kinetic signature of its interstellar origin, accumulated during millions of years of travel through the galaxy under the influence of stellar gravitational fields and galactic rotation. The rarity of confirmed interstellar visitors makes each one precious to science. Before 2017, astronomers had only theoretical models to guide their understanding of how objects might behave during interstellar journeys. 1I/Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. 2I/Borisov appeared more conventionally comet-like but revealed chemical compositions unlike anything in our solar system. Now 3I Atlas adds a third data point to this sparse collection, and early indications suggest it will prove as unique as its predecessors. The object's behavior challenges models in new ways, particularly its unexpectedly large coma and unusual brightness evolution. Each interstellar visitor seems to carry its own set of physical and chemical rules, suggesting that the galaxy harbors far more diversity in small body formation processes than we previously imagined. The classification process involves more than just confirming interstellar status. Astronomers must also determine whether 3I Atlas represents an asteroid-like body, a comet, or something entirely different. The presence of a coma strongly suggests comet-like behavior, but the specific gases and dust compositions revealed through spectroscopic analysis will ultimately determine how this object formed and evolved in its birth star system. This is not a local comet kicked inward from the Oort cloud, that distant reservoir of icy bodies that occasionally sends visitors toward the inner solar system. 3I Atlas formed around another star, condensed from materials that experienced different temperatures, pressures, and chemical environments than anything native to our cosmic neighborhood. It represents a direct sample of planetary formation processes that occurred light years away, possibly billions of years ago. The trajectory calculations place 3I Atlas on a path that will provide unprecedented observation opportunities, particularly during its close approach to Mars on October 3. This geometry isn't accidental. The object's orbital inclination and timing align favorably for spacecraft observations just when Earth-based telescopes will lose sight of it due to solar glare. But understanding what we're seeing requires more than just knowing where 3I Atlas came from and where it's going. The real mysteries lie in how it's behaving as it encounters our Sun's radiation for the first time in its existence and why that behavior differs so dramatically from theoretical predictions. Time is running out for 3I Atlas and for the astronomers racing to understand it before it vanishes into solar glare. The mathematics of orbital mechanics have drawn a precise roadmap through the inner solar system, marking critical dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3, 2025 represents the first crucial milestone. On this date, 3I Atlas will sweep past Mars at a distance of approximately 30 million kilometers, roughly 0.19 to 0.2 astronomical units. In cosmic terms, this constitutes an extremely close encounter, placing the interstellar visitor well within the operational range of multiple spacecraft currently orbiting the red planet. The timing couldn't be more fortuitous or more frustrating. Just as 3I Atlas reaches its closest approach to Mars, offering spacecraft the clearest possible view of an interstellar object in action, Earth-based telescopes begin losing their ability to track it. The cruel geometry of orbital mechanics places the comet increasingly close to the Sun's position in our sky, creating observational challenges that will soon become insurmountable. By late October, specifically October 29 to 30th, 3I Atlas reaches perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. This distance places it just inside Mars's average orbital radius, subjecting the interstellar visitor to solar radiation intensities unlike anything it experienced during its journey through the galaxy. The timing coincides almost perfectly with the period of greatest observational difficulty from Earth. The speed evolution tells its own dramatic story. Currently traveling at tens of kilometers per second, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second or approximately 152,000 miles per hour. To put this in perspective, Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I Atlas will be moving more than twice as fast as our entire planet. These velocities represent more than impressive statistics. They reveal the fundamental physics governing interstellar motion. Unlike objects native to our solar system, which gained their speeds through gravitational interactions with the Sun and planets over billions of years, 3I Atlas carries kinetic energy accumulated during its journey between star systems. Every kilometer per second of velocity represents vast distances traveled through interstellar space, influenced by the gravitational fields of multiple stars and the rotation of the galaxy itself. The approach trajectory places 3I Atlas near the ecliptic plane, the relatively flat disk containing most planetary orbits. This geometry facilitates the close encounter with Mars and will later enable a distant approach to Jupiter in 2026. The orbital alignment isn't coincidental. Objects approaching from random directions in three-dimensional space would be unlikely to pass so conveniently close to multiple planets during their brief transit through our solar system. Safety considerations never entered the equation for 3I Atlas despite its classification as a potentially hazardous object during initial tracking. The closest approach to Earth occurs at approximately 1.8 astronomical units, nearly twice the distance to the Sun and well beyond any conceivable threat. NASA's confirmation of this safe distance eliminated public concern about collision, allowing astronomers to focus on the scientific opportunities rather than planetary defense considerations. The real challenge lies in observational geometry. From early October through early November, 3I Atlas experiences what astronomers call superior conjunction, a period when its position in Earth's sky places it too close to the Sun for practical observation. Solar elongation, the angular separation between the comet and the Sun as seen from Earth, drops below 30 degrees for much of this critical period. Imagine trying to spot a firefly hovering next to a floodlight, and you begin to understand the observational predicament. Even the most sophisticated telescopes cannot separate the faint light of 3I Atlas from the overwhelming glare of our star when the two objects appear close together in the sky. This natural limitation of Earth-based astronomy means that the comet's most active period may occur largely hidden from human observation. The conjunction timing creates a fundamental irony in the 3I Atlas encounter. Just as solar heating reaches its maximum intensity and the comet could potentially undergo its most dramatic transformations, Earth's astronomical community will be effectively blinded. The peak outgassing, possible fragmentation events, and maximum tail development could all occur during the weeks when ground-based telescopes cannot function effectively. This observational gap places extraordinary importance on spacecraft positioned throughout the solar system, particularly those orbiting Mars. The European Space Agency's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly find themselves in the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The post-perihelion timeline offers both hope and realism about what observers can expect. Assuming 3I Atlas survives its solar encounter intact, Earth-based observations should resume in November or early December as solar elongation increases beyond practical limits. However, the comet will likely be fading rapidly by then, having exhausted much of its volatile content during the unobserved peak heating period. Magnitude predictions suggest that even at its brightest, 3I Atlas will remain a telescopic object for Earth-based observers. Peak brightness estimates hover around magnitude 11 to 12, far too faint for naked-eye visibility but well within the range of amateur astronomical equipment. The lack of a spectacular naked-eye show may disappoint casual observers, but it doesn't diminish the scientific value of this unprecedented interstellar encounter. The velocity profile reveals another crucial aspect of the 3I Atlas timeline. As the object approaches perihelion, its speed continues increasing under solar gravitational acceleration. However, immediately after closest approach, that same gravity begins decelerating the comet as it moves away from the Sun. This velocity change affects the duration of peak heating and the time frame available for observation by Mars-based spacecraft. Looking beyond perihelion, the trajectory calculations show 3I Atlas continuing outward through the solar system, eventually approaching Jupiter in March 2026. While this encounter will occur at a much greater distance than the Mars flyby, it may provide additional opportunities for spacecraft observations as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunity that astronomy has never faced before. Unlike periodic comets that return regularly, allowing multiple opportunities for study, 3I Atlas offers a single chance to understand an object from another star system. The observational challenges, conjunction timing, and spacecraft opportunities must all align perfectly for humanity to extract maximum scientific value from this cosmic visitor. As we approach the critical October dates, the question isn't just what 3I Atlas will reveal about itself, but whether our observational capabilities will prove adequate to capture those revelations. The mathematics of orbital mechanics have set the schedule, and that schedule waits for no one. The most astonishing discovery about 3I Atlas isn't its interstellar origin or unusual trajectory. It's the sheer impossible scale of the atmosphere it's creating around itself. In September 2025, NASA's SPHERE-X telescope detected something that defied every model astronomers had constructed for comet behavior: an extended carbon dioxide coma stretching 348,000 kilometers from the nucleus. To grasp the magnitude of this measurement, consider that this ghostly atmosphere extends roughly half the diameter of our Sun. The coma of 3I Atlas has grown large enough to contain Mercury's entire orbit, creating a bubble of gas and dust that dwarfs anything typically observed around comets in our solar system. This isn't just unusual, it's unprecedented in the annals of cometary science. A coma forms when solar radiation heats the ices locked within a comet's nucleus, causing them to sublimate directly from solid to gas without passing through a liquid phase. Think of it as a cosmic snowball steaming in sunlight. But the analogy fails to capture the violence of the process. As frozen materials explosively transition to gas, they carry dust particles and larger debris outward, creating an expanding atmosphere that can grow to enormous proportions. The composition of 3I Atlas's coma tells a story of formation in conditions radically different from our solar system. The dominance of carbon dioxide over water vapor suggests this object condensed in a region where CO2 could freeze out more readily than H2O, possibly in the outer reaches of another star's planetary disk, where temperatures remained low enough for carbon dioxide ice to remain stable while water existed primarily as vapor. This CO2-rich environment hints at the chemical conditions present during 3I Atlas's birth. Most comets in our solar system show water as their primary volatile component, with carbon dioxide playing a secondary role. The reversed ratio observed in 3I Atlas indicates formation temperatures and pressures unlike anything experienced by objects native to our cosmic neighborhood. But the coma's composition isn't its only unusual characteristic. Images from the Hubble Space Telescope and ground-based observatories reveal a structure that challenges fundamental assumptions about comet behavior. Instead of the classic tail streaming away from the Sun, 3I Atlas displays what astronomers call an anti-tail, a plume of material that appears to point sunward. This sunward-pointing structure represents a puzzle that has kept researchers working through sleepless nights. Conventional comet physics dictates that solar radiation pressure should push gas and dust away from the sun, creating the familiar tales that have inspired human imagination for millennia. Yet, 3I Atlas seems to be violating this basic principle, ejecting material in directions that contradict textbook explanations. Hubble's July 21 observations captured what mission scientists described as a forward glow, a fan-shaped structure extending from the nucleus toward the sun rather than away from it. Follow-up imaging by the Gemini South Telescope on August 27 showed this unusual geometry persisting and evolving, suggesting that the anti-tail represents a stable feature rather than a temporary anomaly. The physics behind anti-tail formation involve processes more complex than simple radiation pressure. Large dust grains, too massive to be easily pushed by solar photons, can maintain sunward trajectories if they're ejected from the nucleus with sufficient initial velocity. Additionally, projection effects can make material moving in three-dimensional space appear to point toward the sun when viewed from Earth's specific vantage point. However, theoretical models struggle to explain the persistence and prominence of 3I Atlas's sunward plume. The structure appears too well-defined and long-lasting to result from simple projection effects, while the required dust grain sizes and ejection velocities needed to create such an extensive anti-tail push the boundaries of what's physically reasonable for a comet nucleus. Recent analysis suggests that the anti-tail might result from unusual rotation states or surface properties unique to interstellar objects. A slowly spinning nucleus could maintain temperature differences between its day and night sides that concentrate outgassing in specific directions. Alternatively, the surface composition of 3I Atlas might include materials that respond to solar heating in ways unfamiliar to researchers accustomed to studying local comets. The comet's expansion rate adds another layer to the mystery. Spectroscopic observations indicate that gas velocities within the coma exceed typical values for comets at similar distances from the Sun. This enhanced outgassing could result from the release of supervolatile compounds that remain stable only in interstellar conditions, sublimating rapidly when first exposed to significant solar heating. Temperature measurements of the coma reveal additional anomalies. The gas temperatures recorded by infrared observations suggest heating mechanisms beyond simple solar absorption. Possible explanations include chemical reactions between previously separated compounds or the release of energy stored in exotic ice crystal structures that formed under interstellar conditions. The three-dimensional structure of the coma, reconstructed from multiple viewing angles and different wavelengths of light, shows asymmetries that point to non-uniform outgassing from the nuclear surface. Rather than the relatively symmetric comas typical of well-studied comets, 3I Atlas displays jets and fans of material emerging from specific regions of its nucleus. These jets suggest that the nuclear surface contains discrete areas of volatile-rich material, possibly exposed by impacts or thermal cycling during the object's interstellar journey. The pattern of outgassing could preserve information about the comet's formation environment and subsequent evolution during millions of years of travel through space. Dust analysis within the coma reveals particle-size distributions unlike those found in solar system comets. The abundance of large grains necessary to create the observed anti-tail structure suggests that 3I Atlas either formed with different dust-to-ice ratios than local comets or that its dust particles have undergone modification processes during interstellar transit. The expansion dynamics show temporal variations that correlate with the comet's distance from the Sun and potentially with rotation periods. As 3I Atlas continues its approach toward perihelion, the coma continues growing and evolving, potentially reaching even larger dimensions as solar heating intensifies. Modeling efforts to predict the coma's future evolution face unprecedented challenges. The unusual composition, anti-tail geometry, and enhanced outgassing rates all require modifications to standard cometary physics models. Researchers are effectively developing new theoretical frameworks in real time as observations continue to reveal unexpected behaviors. The implications extend beyond 3I Atlas itself. If interstellar comets routinely display such unusual coma characteristics, it suggests that our understanding of comet physics, based primarily on objects native to our solar system, may represent only a narrow subset of possible behaviors. Each interstellar visitor could force revisions to fundamental assumptions about how these objects form and evolve. As 3I Atlas approaches its critical encounters with Mars and the Sun, the comet's continued expansion and structural evolution will provide crucial tests of competing theoretical models. The question is whether the most dramatic changes will occur during the observational gap when Earth's telescopes cannot track the comet's behavior. But the comet's evolution represents only one aspect of 3I Atlas's transformation as it encounters our Sun's radiation. The most visually striking change occurred in mid-September when the entire comet began glowing with an eerie green light that signaled chemistry unlike anything previously observed in an interstellar visitor. In the middle of September 2025, 3I Atlas did something that sent ripples of excitement through the astronomical community. It turned green. Not gradually, not subtly, but with a vivid emerald glow that transformed this interstellar visitor from a pale smudge into something that looked almost alive against the star-filled darkness. The color change wasn't immediately obvious to casual observers. 3I Atlas remains too faint for naked-eye visibility. But sensitive cameras attached to telescopes around the world began capturing images that showed an unmistakable green tint surrounding the comet's nucleus. The transformation became particularly evident in photographs taken during the lunar eclipse on September 14, when the moon's shadow provided darker skies that enhanced the contrast of the comet's newfound luminescence. The green glow tells a story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the sun, their electrons jump to higher energy states. As these electrons fall back to their ground state, they emit light at specific wavelengths that our eyes perceive as distinct colors. In the case of 3I Atlas, the green emission most likely originates from diatomic carbon, two carbon atoms bonded together, designated as C2 in chemical notation. Diatomic carbon behaves like a molecular neon sign in space. When energized by solar ultraviolet radiation, C2 molecules emit light at wavelengths around 516 nanometers, producing the characteristic green glow that has made 3I Atlas one of the most visually distinctive comets observed in recent years. This emission process, called fluorescence, transforms invisible solar energy into visible light that can travel across millions of kilometers to reach Earth-based telescopes. But here's where the story becomes puzzling. Early spectroscopic observations of 3I Atlas showed relatively little evidence for carbon-bearing compounds. The initial chemical analysis suggested a composition dominated by carbon dioxide and water vapor, with only trace amounts of the carbon-rich molecules typically responsible for green comet colors. This apparent contradiction between the observed green glow and the measured chemical composition has researchers scrambling to understand what's really happening in the comet's expanding atmosphere. One possibility involves phase transitions in the comet's outgassing behavior. As 3I Atlas moved closer to the Sun and crossed the 2 astronomical unit threshold in early September, increased solar heating may have begun sublimating previously inaccessible deposits of carbon-rich materials within the nucleus. These materials, locked away in the comet's interior during its long interstellar journey, might now be experiencing solar radiation for the first time in their existence. The timing of the green color change correlates suspiciously well with the period of rapid brightening observed in mid-September. This suggests that the same physical processes responsible for the unexpected brightness surge, possibly the catastrophic release of volatile materials from subsurface reservoirs, also triggered the chemical reactions producing the green emission. Alternative explanations for the color shift involve more complex chemistry than simple diatomic carbon fluorescence. Comets can contain dozens of different carbon-bearing molecules, each with its own emission characteristics. The apparent green glow might result from a blend of emissions from multiple species or from carbon-containing molecules unique to interstellar environments that don't exist in significant quantities among solar system comets. Instrument sensitivity and processing techniques also introduce uncertainty into color measurements. Different telescopes using different filters and imaging systems can produce subtly different color renditions of the same object. What appears distinctly green in one image might look more blue-green or yellow-green in another, depending on the specific wavelengths recorded and the methods used to combine them into color images. The evolution of the green glow provides additional clues about the underlying chemistry. Unlike the steady emission expected from simple molecular fluorescence, observations suggest that the green color varies in intensity and distribution within the coma. Some regions appear more intensely green than others, suggesting that carbon-bearing molecules aren't uniformly distributed throughout the expanding gas cloud. This non-uniform distribution could result from discrete outgassing events, where jets of material erupting from specific locations on the nucleus carry different chemical compositions. Alternatively, the variation might reflect chemical processing within the coma itself as solar ultraviolet radiation breaks down complex organic molecules into simpler fragments that fluoresce at different wavelengths. The green emission also provides a diagnostic tool for understanding the physical conditions within the coma. The intensity of molecular fluorescence depends on the density of molecules, their temperature, and the intensity of solar ultraviolet radiation. By measuring how the green glow varies with distance from the nucleus and changes over time, researchers can map the three-dimensional structure of the carbon-bearing gas within 3I Atlas's atmosphere. Temperature measurements derived from the green emission characteristics suggest that the carbon-bearing molecules exist in a state of thermal equilibrium with the rest of the coma gases. This indicates efficient energy transfer between different molecular species, providing insights into collision rates and gas dynamics within the expanding atmosphere. The appearance of green coloration in 3I Atlas adds another data point to the growing catalog of differences between interstellar visitors and native solar system objects. 1I/Oumuamua showed no clear signs of cometary activity and thus no color changes. 2I/Borisov displayed more conventional comet colors dominated by blue and white scattered sunlight rather than molecular emission lines. 3I Atlas represents the first interstellar comet to develop the classic green coma that amateur astronomers associate with approaching periodic comets. However, the specific wavelengths and intensity of the green emission may differ subtly from those of familiar comets, potentially revealing chemical compositions unique to objects formed in other star systems. The timing of the color change creates additional observational urgency. As 3I Atlas approaches superior conjunction and becomes unobservable from Earth in early October, the green emission may continue evolving or could fade entirely. The peak intensity of molecular fluorescence often occurs near perihelion when solar heating reaches its maximum, but this critical period will be largely hidden from Earth-based telescopes. Spectroscopic follow-up observations will attempt to identify the specific molecules responsible for the green emission. But these measurements require large telescopes and favorable observing conditions that become increasingly difficult to achieve as the comet approaches the sun's glare. Each night of clear weather becomes precious as astronomers race to characterize the emission before losing sight of their target. The green glow transformation represents more than just a visually striking development. It provides direct evidence that 3I Atlas is undergoing fundamental chemical changes as it encounters our sun's radiation. The molecules now fluorescing in the comet's coma have likely remained chemically inert for millions of years, preserved in frozen silence during the object's journey between star systems. Now, for the first time since its formation, 3I Atlas is literally lighting up as solar energy activates chemical processes that have been dormant since the comet's birth around another star. The green glow marks the awakening of alien chemistry, the first stirrings of molecular activity in materials that formed under conditions possibly unlike anything in our solar system. But observing this awakening presents challenges that push the limits of ground-based astronomy, challenges that will soon force researchers to rely on mechanical eyes positioned throughout the solar system to continue monitoring our transformed interstellar visitor. The universe has a cruel sense of timing when it comes to 3I Atlas. Just as this interstellar visitor begins revealing its most intriguing secrets, the rapid brightening, the impossible coma, the alien green glow, the mechanics of orbital geometry conspire to snatch it away from Earth-based observers at the most critical moment of its journey. Professional telescopes equipped with the most sophisticated instruments humanity can build face the same fundamental limitation that frustrates backyard astronomers. You cannot observe what hides behind the sun's location. As 3I Atlas continues its approach toward perihelion, its position in Earth's sky moves inexorably closer to our star's overwhelming glare, creating observational challenges that no amount of technological advancement can overcome. The James Webb Space Telescope managed to capture spectroscopic observations of 3I Atlas on August 6, using its near-infrared spectrograph, providing crucial chemical composition data during one of the few windows when the world's most advanced observatory could safely point toward the comet without risking solar damage. These observations represent some of the most detailed chemical analysis possible for an interstellar object, but they occurred before the dramatic changes of mid-September that transformed 3I Atlas from a merely unusual comet into an actively puzzling one. The Hubble Space Telescope contributed its own observations on July 21, capturing high-resolution images that revealed the sunward-pointing plume structure and provided size constraints for the nucleus. However, since August, new high-resolution imagery from major space-based observatories has become sparse. The observatories that can provide the detailed analysis necessary to understand 3I Atlas's unusual behavior are the same ones most vulnerable to solar interference as the comet approaches conjunction. Ground-based observatories face their own cascade of complications. Different telescopes using different filter systems and calibration procedures produce brightness measurements that don't always agree with each other. This inconsistency isn't unusual in astronomy. Brightness measurement, or photometry, requires careful attention to atmospheric conditions, instrument calibration, and standardization procedures that can vary between observatories. The Comet Observation Database attempts to reconcile these differences by collecting brightness reports from observers worldwide and plotting them against theoretical models. Throughout September, the COBS data clearly showed 3I Atlas trending brighter than predicted, with measured magnitudes consistently above the expected curve. But the scatter in individual measurements reflects the challenges faced by observers trying to track a rapidly changing object that defies their carefully constructed models. Amateur astronomers, often working with smaller telescopes and less sophisticated equipment, contribute valuable long-term monitoring data that professional observatories cannot always provide. However, their measurements face additional uncertainties from atmospheric turbulence, light pollution, and equipment limitations. The result is a patchwork of observations that collectively paint a picture of unusual behavior while individually containing enough uncertainty to fuel debates about what's really happening. The SkyLive and other tracking websites compile these diverse observations into light curves that show brightness evolution over time. The sites that track 3I Atlas consistently show the same troubling trend, measured brightness points climbing above the predicted trajectory, particularly after mid-September. Yet the precise magnitude of this deviation remains uncertain due to the inherent challenges in measuring faint, rapidly changing objects. Solar elongation, the angular separation between 3I Atlas and the Sun as seen from Earth, represents the fundamental constraint limiting all observations. As this angle decreases below 30 degrees, even the most powerful telescopes struggle to separate the comet's faint light from scattered sunlight in Earth's atmosphere. Professional observatories typically cease observations when elongation drops below 20 degrees, while amateur observers may lose the object even earlier due to equipment limitations and local observing conditions. The elongation timeline creates a countdown that no human technology can extend. In early October, 3I Atlas drops below the 30 degrees threshold that marks the beginning of serious observational difficulties. By mid-October, elongation decreases to less than 20 degrees, effectively ending routine observations from Earth's surface. This period of invisibility extends through early November, encompassing the critical weeks when solar heating reaches its maximum intensity. The irony is palpable. We're trying to watch a cosmic firefly hovering next to a floodlight using instruments designed to detect the faintest whispers of light from the most distant galaxies. Even adaptive optic systems that can compensate for atmospheric turbulence and coronagraphs designed to block stellar light cannot overcome the fundamental physics of scattered sunlight when the comet appears too close to the Sun's position in the sky. Space-based observatories theoretically possess advantages over ground-based telescopes in dealing with solar interference, but they face their own constraints. Instruments like Hubble and James Webb include protective systems that prevent them from pointing too close to the Sun, automatically shutting down observations when solar angles become dangerous. These safety systems, essential for preventing catastrophic damage to billion-dollar instruments, create observation gaps precisely when they would be most valuable. The timing of 3I Atlas's conjunction period couldn't be worse for understanding its peak activity. Theoretical models predict that maximum outgassing, possible fragmentation events, and the most dramatic tail development should all occur near perihelion in late October. These are exactly the phenomena that could reveal the most about 3I Atlas's composition, structure, and origins, and they will occur largely hidden from human observation. Data processing challenges compound the observational difficulties. Images of 3I Atlas must be carefully processed to separate the comet signal from background stars, cosmic rays, and instrumental artifacts. As the object becomes fainter relative to sky brightness during its approach to conjunction, these processing steps become increasingly critical and increasingly spectroscopic observations, essential for understanding the chemical composition of the comet's coma and tail, require even more specialized conditions than simple brightness measurements. The instruments needed to disperse comet light into its component wavelengths work best with bright targets observed under dark skies. As 3I Atlas fades into solar glare, opportunities for detailed spectroscopic analysis vanish just when chemical activity may be reaching its peak. The atmospheric limitations affect different wavelengths of light in different ways. Ultraviolet emissions, crucial for detecting many molecular species in comet comas, become particularly difficult to observe as elongation decreases because Earth's atmosphere scatters blue and ultraviolet light more efficiently than red wavelengths. This scattering effect, which gives our sky its blue color, creates additional challenges for studying the chemical processes occurring within 3I Atlas's expanding atmosphere. Coordination between observatories becomes essential as observing conditions deteriorate. Facilities at different latitudes and in different time zones must work together to maximize the limited observation windows available each night. Southern Hemisphere observatories may retain better viewing geometry slightly longer than their northern counterparts, creating opportunities for extended monitoring that require careful international coordination. The photometric scatter in brightness measurements reflects more than instrumental limitations. It may also indicate real variability in 3I Atlas's output. Comets can undergo rapid changes in brightness due to outgassing events, rotation effects, or structural changes in their nuclei. Distinguishing between measurement uncertainty and genuine comet variability becomes increasingly difficult as signal-to-noise ratios decrease during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities that will not recur. Unlike periodic comets that return predictably, 3I Atlas offers only a single passage through the inner solar system, making each clear night precious and irreplaceable. The challenge extends beyond individual observations to the broader question of how to interpret the data that does exist. The brightness trend showing 3I Atlas exceeding predicted values could indicate enhanced outgassing, structural changes, or simply systematic errors in the theoretical models used for comparison. Resolving these questions requires the kind of detailed long-term monitoring that becomes impossible as the comet disappears into solar glare. As Earth-based astronomy reaches its limits in observing 3I Atlas, the responsibility for continued monitoring shifts to mechanical eyes positioned throughout the solar system. Spacecraft orbiting Mars, designed for entirely different missions, suddenly find themselves serving as humanity's primary observers of one of the most significant astronomical events of the decade. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching excitement and, yes, alarm ripples through the global community of comet researchers. 3I Atlas isn't behaving according to the scripts written by decades of cometary science, and astronomers are beginning to admit, in the cautious way that scientists acknowledge uncertainty, that they might be witnessing something unprecedented. The brightness trend, documented by observers worldwide, represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I Atlas consistently outshining the predictions derived from standard cometary models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometary scientist who has spent his career studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile release mechanisms in comets. The speed of the change, he suggested, indicates processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers, the recognition that they might be observing phenomena that will require new theoretical frameworks to understand. Earth sky tracking reporting on 3I Atlas captures this tension, describing observations that continue to surprise researchers while acknowledging that much of what appears unusual might reflect the inherent unpredictability of objects formed in other star systems. The sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena aren't unknown in cometary science, but the persistence and prominence of 3I Atlas's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust grain compositions, non-uniform nucleus rotation, exotic volatile mixtures, to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3I Atlas is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun. The carbon dioxide-dominated coma detected by SphereX, extending to unprecedented distances, suggests outgassing rates that exceed standard predictions by significant margins. This isn't subtle deviation from theory, it's a dramatic departure that demands explanation. Yet, the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained unusual behavior. Comets are notoriously prone to sudden brightness surges followed by equally rapid returns to predicted levels. The question haunting 3I Atlas observations is whether the September brightening represents a genuine departure from normal behavior or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap. The most critical period for understanding 3I Atlas's true nature, the week surrounding perihelion, when solar heating reaches maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never understand what they witnessed in September. Dr. Carrie Holt, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3I Atlas might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what she termed a cosmic conspiracy against scientific understanding. The debates extend beyond simple brightness measurements to fundamental questions about what 3I Atlas represents as a physical object. Its chemical composition, revealed through spectroscopic analysis, shows ratios of carbon dioxide to water vapor unlike those typical of solar system comets. This difference could indicate formation conditions radically different from our local environment, or it might reflect chemical processing that occurred during millions of years of interstellar travel. Amateur astronomy communities have become crucial contributors to the 3I Atlas monitoring effort, providing continuous observations that professional observatories cannot always maintain. However, the scattered nature of amateur measurements introduces its own complications. Different observers using different equipment and processing techniques sometimes report brightness values that disagree by significant amounts, making it challenging to determine whether observed variations represent real changes in the comet or measurement artifacts. The European Space Agency's tracking efforts, coordinated through their Space Situational Awareness Program, attempt to reconcile these measurement discrepancies while maintaining continuous monitoring of 3I Atlas's trajectory and brightness evolution. Their analysis confirms the general trend toward enhanced brightness but acknowledges the difficulties in quantifying exactly how much the comet exceeds theoretical predictions. Social media within the astronomical community reflects a mixture of scientific excitement and professional caution that characterizes the response to 3I Atlas. Researchers share preliminary images and brightness measurements while carefully noting the uncertainties and limitations in their data. The tone suggests scientists are aware they're observing something potentially significant while remaining professionally skeptical about drawing premature conclusions. The green color change documented in mid-September adds another layer to the scientific intrigue. While diatomic carbon emission can explain the observed coloration, the timing and intensity of the green glow don't perfectly match the chemical composition indicated by earlier spectroscopic observations. This apparent discrepancy between what researchers measure chemically and what they observe visually suggests either measurement limitations or chemical processes more complex than standard models predict. Conference presentations scheduled for the American Astronomical Society's Division for Planetary Sciences meeting include multiple talks focused on 3I Atlas observations and theoretical modeling efforts. The abstracts reveal research groups worldwide attempting to understand not just what 3I Atlas is doing but why existing models fail to predict its behavior accurately. The sense of urgency among researchers reflects more than scientific curiosity. It represents the recognition that opportunities to study interstellar objects remain extraordinarily rare. With only 3 confirmed interstellar visitors in human history, each object provides irreplaceable data about conditions in other star systems and the processes that govern small body formation throughout the galaxy. International collaboration has intensified as the observational window narrows. Telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinate observations to maximize coverage as 3I Atlas approaches the solar conjunction period that will end routine Earth-based monitoring. Each facility contributes unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, in an effort to extract maximum scientific value from the remaining observation opportunities. The professional astronomical community also grapples with public communication challenges surrounding 3I Atlas. Media reports sometimes overstate the certainty of scientific conclusions or sensationalize aspects of the comet's behavior that researchers themselves acknowledge as uncertain. Balancing public interest in this rare interstellar visitor with the inherent uncertainties of ongoing research requires careful attention to how findings are presented and interpreted. Risk assessment models developed for potentially hazardous asteroids receive new attention in the context of 3I Atlas, not because the comet poses any danger to Earth, but because its unpredictable behavior highlights limitations in current understanding of how small bodies behave under solar heating. If researchers cannot accurately predict the behavior of 3I Atlas, questions arise about the reliability of models used to assess risks from other objects. The excitement building around 3I Atlas reflects a fundamental aspect of scientific discovery: the recognition that nature consistently produces phenomena more complex and surprising than human theories predict. As October approaches and Earth-based observations become increasingly difficult, astronomers find themselves hoping that spacecraft positioned throughout the solar system might capture the revelations that ground-based telescopes will be forced to miss. While Earth prepares to lose sight of 3I Atlas in the solar glare, another world positions itself for a front-row seat to one of the most significant astronomical events in recent memory. On October 3, 2025, Mars will host humanity's closest encounter with an interstellar visitor, offering spacecraft orbiting the red planet unprecedented opportunities to observe 3I Atlas from a vantage point Earth-based telescopes can only dream of achieving. The geometry couldn't be more fortuitous. As 3I Atlas sweeps past Mars at a distance of approximately 30 million kilometers, roughly 0.2 astronomical units, multiple spacecraft currently operational in Martian orbit will have the opportunity to turn their instruments toward this cosmic visitor. The timing places these observations just days before superior conjunction makes Earth-based tracking impossible, creating a crucial handoff from terrestrial to space-based monitoring. The European Space Agency's Mars Express orbiter, launched in 2003 and still functioning far beyond its original mission timeline, carries the high-resolution stereo camera that has mapped Martian terrain in unprecedented detail for over 2 decades. While designed for planetary geology, HRSC possesses the sensitivity and resolution potentially needed to capture detailed images of 3I Atlas's nucleus and inner coma structure. Dr. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, confirmed that mission planners are evaluating opportunities for both the color and stereo surface imaging system, known as CASIS, and the nadir and occultation for Mars Discovery Spectrometer, NOMAD, to observe the interstellar visitor. These instruments, designed to study Martian atmospheric composition and surface features, might be capable of detecting chemical signatures within 3I Atlas's expanding coma. NASA's Mars Reconnaissance Orbiter presents perhaps the most intriguing possibilities for detailed observations. The high-resolution imaging science experiment, HiRISE, routinely captures surface details smaller than 1 meter across from its orbital altitude of roughly 300 kilometers above Mars. While 3I Atlas will pass much farther away, HiRISE's extraordinary resolution might resolve structural details of the comet's nucleus that remain invisible to Earth-based telescopes. The MAVEN spacecraft, NASA's Mars Atmosphere and Volatile Evolution mission, carries spectrographic instruments specifically designed to analyze atmospheric composition and dynamics. These capabilities could prove valuable for studying the chemical composition of 3I Atlas's coma, particularly the carbon dioxide-rich gases that dominate its spectroscopic signature. However, the observational opportunities come with significant technical challenges. All Mars orbiters were designed and optimized for studying the red planet itself, not for tracking fast-moving objects against the stellar background. The spacecraft's pointing systems, developed for observing a large nearby planet, must be reconfigured to follow a small, distant target moving at interstellar velocities. Signal strength represents the most fundamental limitation. Even at its closest approach to Mars, 3I Atlas will appear extremely faint to spacecraft instruments designed for planetary rather than deep space observations. The comet's magnitude, estimated around 12 to 14, even during its brightening phase, pushes the detection limits of most Mars orbiter cameras and spectrometers. Dr. Wilson acknowledged these limitations in recent communications with the international astronomical community, noting that while Mars-based observations of 3I Atlas are theoretically possible, the actual scientific return depends on factors including the comet's brightness at closest approach, atmospheric conditions on Mars, and the specific geometric arrangements required for successful pointing. The advantage of Mars-based observations extends beyond simple proximity. The viewing geometry from Mars during the October 3 flyby provides a perspective on 3I Atlas unavailable from Earth. Solar phase angles, the angle between the Sun, comet, and observer, will differ significantly between Mars and Earth viewpoints, potentially revealing details of coma structure and tail geometry hidden from terrestrial telescopes. Solar-wind interactions present another area where Mars orbiters might contribute unique observations. 3I Atlas's encounter with the solar wind, the stream of charged particles flowing outward from the Sun, could produce phenomena detectable by the plasma and magnetic field instruments carried by several Mars missions. These interactions might reveal information about the comet's internal structure and composition through changes in its magnetic and electrical properties. The European Space Agency's coordination efforts for the Mars flyby observations involve unprecedented cooperation between missions designed for entirely different scientific objectives. Mars Express, originally planned for surface geology and atmospheric studies, finds itself repurposed as an interstellar object observatory. The Trace Gas Orbiter, focused on methane detection and atmospheric chemistry, must adapt its instruments for cometary spectroscopy. Timing constraints add complexity to observation planning. Mars orbiters follow predetermined schedules for routine planetary observations, communication windows with Earth, and spacecraft maintenance activities. Inserting 3I Atlas observations into these schedules requires careful coordination to avoid conflicts with primary mission objectives while maximizing scientific opportunities. The data transmission challenges are substantial. Mars orbiters typically communicate with Earth during specific windows when both planets' orbits provide favorable geometry for radio transmission. Images and spectra of 3I Atlas must compete with routine planetary science data for limited communication bandwidth, potentially delaying the release of observations by weeks or months. Ground-based support for Mars orbiter observations requires coordination between multiple space agencies and research institutions worldwide. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, and other facilities must work together to plan observation sequences, process incoming data, and distribute results to the international scientific community. The scientific value of successful Mars-based observations could prove transformative for understanding 3I Atlas. High-resolution imaging might resolve the nucleus size and shape with unprecedented precision, settling debates about the comet's physical dimensions and structure. Spectroscopic observations could detect molecular species invisible from Earth-based telescopes, revealing chemical compositions that preserve information about the comet's formation environment. Structural details of the coma and tail, particularly the unusual sunward-pointing plume that has puzzled researchers, might become clearer when viewed from Mars's unique perspective. The different solar phase angle could reveal whether the anti-tail structure results from genuine sunward ejection of material or represents a projection effect that appears different from various viewing angles. Reality requires managing expectations about what Mars orbiters can achieve. Even under optimal conditions, the scientific return from these observations will likely consist of a handful of images and spectra rather than comprehensive monitoring campaigns. The instruments were never designed for this type of observation, and their capabilities may prove insufficient to answer the fundamental questions about 3I Atlas's nature and behavior. Success depends on variables beyond human control. If 3I Atlas undergoes another brightening event before October 3, it might become detectable to Mars orbiter instruments that would otherwise find it too faint to observe. Conversely, if the comet fades from its current enhanced brightness levels, even the most optimistic observation scenarios might yield no useful data. The Mars flyby represents humanity's best opportunity to maintain surveillance of 3I Atlas during the critical weeks when Earth-based telescopes lose sight of this interstellar visitor. As terrestrial astronomy prepares for an imposed silence lasting through early November, the mechanical eyes orbiting Mars offer the only hope of witnessing what may prove to be the most dramatic phase of 3I Atlas's encounter with our solar system. Whether these observations succeed or fail, they mark a new chapter in how humanity studies visitors from other star systems, demonstrating our growing capability to coordinate observations across multiple worlds, even as the objects of our attention race past at interstellar velocities. The mathematics of celestial mechanics are utterly indifferent to human curiosity. As October progresses and 3I Atlas continues its relentless approach toward the Sun, the geometric realities of orbital motion conspire to snatch away our interstellar visitor precisely when it might reveal its most profound secrets. Superior conjunction, that period when 3I Atlas appears too close to the Sun's position in our sky for practical observation, transforms one of the most significant astronomical events in recent memory into a cosmic vanishing act. The timeline unfolds with merciless precision. In early October, 3I Atlas drops below 30 degrees of solar elongation, the threshold where serious observational difficulties begin for ground-based telescopes. Atmospheric scattering of sunlight creates a brightening sky background that overwhelms the faint signal from our interstellar visitor. Professional observatories with their sophisticated adaptive optics and light-gathering power can extend observations slightly longer than amateur telescopes, but even they face increasingly hopeless conditions. By mid-October, elongation decreases to less than 20 degrees, effectively ending routine observations from Earth's surface. The comet doesn't disappear suddenly. It fades gradually into the solar glare like a star at sunrise, becoming increasingly difficult to detect until observation becomes impossible rather than merely challenging. This gradual transition makes it difficult to pinpoint exactly when Earth loses sight of 3I Atlas, but the practical result remains the same. Our primary window into the comet's behavior closes just as solar heating approaches its maximum intensity. This conjunction period extends through early November, encompassing roughly 4 to 5 weeks when 3I Atlas remains effectively invisible from Earth. This isn't simply an inconvenient gap in observations, it represents the complete loss of our ability to monitor the comet during what theoretical models predict should be its most active period. Peak outgassing, maximum tail development, possible fragmentation events, and other dramatic phenomena could all occur hidden from human view. The cruel irony becomes more apparent when considered against the backdrop of 3I Atlas's recent behavior. The rapid brightening observed in September, the unusual anti-tail structure, and the distinctive green coloration all suggest an object undergoing fundamental changes as it encounters our Sun's radiation. Logic dictates that these transformations should intensify as solar heating increases, potentially reaching spectacular levels near perihelion in late October. Yet, perihelion occurs almost exactly at the midpoint of the conjunction period, when 3I Atlas appears closest to the Sun in Earth's sky and observation becomes most impossible. It's as if the universe deliberately arranged for the most interesting part of the show to occur behind a drawn curtain. The physics behind superior conjunction involve no conspiracy against scientific discovery, merely the geometric consequences of observing from a planet orbiting the same star as our target. As 3I Atlas approaches perihelion, its apparent position in the sky necessarily approaches the Sun's location. The angular separation decreases steadily until the comet appears to pass behind our star, creating observational conditions that no amount of technological sophistication can overcome. Professional astronomers face this limitation with frustrating regularity when studying objects that approach close to the Sun. Solar observing satellites like the Solar and Heliospheric Observatory, SOHO, can sometimes track comets during conjunction periods using coronagraphs that block the sun's direct light. However, 3I Atlas's trajectory doesn't pass close enough to the sun for detection by these specialized instruments, which typically observe objects within a few solar radii of our star. The conjunction gap creates unprecedented challenges for a scientific community accustomed to continuous monitoring capabilities. Modern astronomy relies heavily on long-term observation campaigns that track objects through complete cycles of activity. Comets, in particular, require extended monitoring to distinguish between temporary outburst events and sustained changes in behavior. The forced observational hiatus during 3I Atlas's most critical period eliminates the possibility of this type of comprehensive analysis. Spacecraft positioned throughout the solar system offer limited alternatives to ground-based observations, but their capabilities remain constrained by original mission designs focused on planetary rather than cometary studies. The Mars orbiters discussed earlier provide the most promising near-term opportunities, but their observations will be brief snapshots rather than the continuous monitoring needed to fully understand 3I Atlas's evolution. The European Space Agency's Bepi-Colombo mission, currently en route to Mercury, follows a trajectory that might provide occasional opportunities to observe 3I Atlas from a different vantage point than Earth. However, the spacecraft's instruments are optimized for Mercury studies, and the geometric requirements for comet observations may not align favorably with mission operational constraints. NASA's Parker Solar Probe, designed to study the Sun's corona and solar wind, operates in the inner solar system, where it might theoretically encounter 3I Atlas's tail or coma material. However, the probe's highly elliptical orbit and focus on solar rather than cometary phenomena limit its utility for systematic comet observations. The conjunction period also creates challenges for theoretical modeling efforts attempting to predict 3I Atlas's behavior. Computer simulations of comet activity rely on observational data to calibrate their predictions and validate their accuracy. The 4 to 5 week gap in observations eliminates crucial data points that modelers need to refine their understanding of how this interstellar object responds to solar heating. When Earth-based observations resume in November or early December, 3I Atlas will likely have changed dramatically from the object astronomers studied in September. The comet may have brightened further, possibly developing spectacular tail structures visible through amateur telescopes. Alternatively, it might have faded significantly if volatile materials became depleted during the unobserved perihelion passage. More dramatically, 3I Atlas might have fragmented into multiple pieces during its closest approach to the Sun. Comet fragmentation isn't uncommon near perihelion, where tidal forces and thermal stresses can overcome the weak gravitational binding holding nucleus materials together. If fragmentation occurs during conjunction, Earth-based observers will face the challenging task of identifying and tracking multiple objects when observations become possible again. The resumption of observations in late November or December will require careful planning and coordination among observatories worldwide. 3I Atlas will emerge from conjunction in a different region of the sky, requiring telescopes to locate and reacquire the comet after weeks of invisibility. The object's brightness, position, and appearance may have changed sufficiently to complicate identification and tracking efforts. Public interest in 3I Atlas faces its own conjunction-related challenges. Media coverage of astronomical events typically relies on dramatic images and continuous updates to maintain audience engagement. The forced silence during the conjunction period eliminates the steady stream of new observations that sustain public attention, potentially reducing interest just as the comet experiences its most significant transformations. Educational opportunities also suffer during the conjunction gap. Schools and amateur astronomy groups often use bright comets as tools for teaching about solar system dynamics and observational techniques. 3I Atlas's disappearance into solar glare eliminates these opportunities during what might be the comet's most photogenic period, when tail development and nuclear activity could provide the most visually spectacular educational content. The conjunction period serves as a reminder of astronomy's fundamental limitations despite centuries of technological advancement. Humans remain bound to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun. Even our most sophisticated space-based telescopes cannot completely overcome these limitations when objects approach too close to our star. As 3I Atlas vanishes into solar glare, the astronomical community prepares for a period of speculation and theoretical modeling based on incomplete data. The question isn't whether the comet will change during its hidden passage, it's whether those changes will be comprehensible when observations resume or whether the conjunction gap will leave permanent mysteries about what happened during the most critical phase of this interstellar visitor's encounter with our Sun. Deep within the solar glare that blinds Earth's telescopes, 3I Atlas prepares for its appointment with destiny. On October 29 to 30, 2025, this interstellar wanderer will reach perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Hidden from human observation, the comet will experience solar radiation intensities unlike anything in its multi-million-year journey between star systems, potentially undergoing transformations that could redefine our understanding of interstellar objects. The speed evolution alone tells a story of cosmic violence. Currently racing through space at tens of kilometers per second, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second, or approximately 152,000 miles per hour. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I Atlas will be moving more than twice as fast as our entire planet, carrying kinetic energy accumulated during its epic journey across the galaxy. Physics predicts that perihelion will trigger the most dramatic phase of 3I Atlas's solar system encounter. As solar heating reaches maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have remained stable throughout its interstellar voyage. Water ice, carbon dioxide, carbon monoxide, and more exotic frozen gases could all begin sublimating simultaneously, creating an explosive expansion of the coma that might dwarf the already unprecedented dimensions observed in September. The increased outgassing could produce spectacular dust jets erupting from discrete locations on the nuclear surface. These jets, formed when subsurface volatile deposits find pathways to escape, can create fountain-like structures extending thousands of kilometers into space. The sunward-pointing anti-tail that has puzzled observers might intensify dramatically, or entirely new tail structures could emerge as different volatile compounds begin contributing to the coma for the first time. Theoretical models suggest that 3I Atlas's carbon dioxide-rich composition might produce perihelion behavior unlike that of typical solar system comets. Carbon dioxide sublimes more readily than water ice at the temperatures expected near perihelion, potentially creating gas production rates that exceed those of water-dominated comets by significant factors. This enhanced activity could manifest as rapid changes in brightness, coma size, and tail structure occurring over periods of hours rather than the days or weeks typically associated with comet evolution. The possibility of fragmentation looms over perihelion predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their icy matrices. The thermal stresses induced by intense solar heating, combined with the mechanical forces generated by explosive outgassing, can overcome these binding forces and tear nuclei apart. Fragmentation events can unfold with dramatic suddenness. A comet that appears stable during its approach to perihelion can split into multiple pieces within hours as thermal gradients create structural weaknesses or gas pressure eruptions excavate material from the nucleus interior. If 3I Atlas undergoes fragmentation, Earth-based observers will face the complex task of identifying and tracking multiple objects when observations resume in November. The historical precedent for comet fragmentation near perihelion includes spectacular examples like Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces before impacting the planet in 1994. More recently, Comet Ison disintegrated during its extremely close approach to the Sun in 2013, creating a debris cloud that dispersed rapidly as it moved away from perihelion. However, fragmentation isn't inevitable. The structural integrity of 3I Atlas depends on factors including nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique volatile mixture. Interstellar objects might possess structural characteristics that differ significantly from solar system comets, potentially making them more or less susceptible to thermal disruption. The speed at which 3I Atlas passes through perihelion also influences fragmentation risk. Unlike some comets that linger near their closest solar approach, 3I Atlas will sweep past perihelion relatively quickly due to its hyperbolic trajectory. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If 3I Atlas survives perihelion intact, the post-perihelion period should reveal an object transformed by its encounter with intense solar radiation. The coma might expand to even larger dimensions as peak gas production rates distribute material across unprecedented volumes of space. New chemical species, liberated from subsurface deposits by deep heating, could appear in spectroscopic observations for the first time. Color changes beyond the green emission already observed might develop as different molecular species begin fluorescing under solar ultraviolet radiation. Complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions across the visible spectrum. The anti-tail phenomenon that has characterized 3I Atlas observations might evolve dramatically near perihelion. Enhanced dust production could create multiple tail structures pointing in different directions as particles of various sizes respond differently to solar radiation pressure. The resulting geometry could provide crucial information about the nucleus rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period. The size distribution and composition of particles ejected from the nucleus reflect the internal structure and formation conditions of the original object. Large grains might indicate a loosely consolidated nucleus with significant void spaces, while fine dust could suggest a more compact structure or specific chemical compositions that favor the production of small particles. The magnetic and plasma environment near perihelion adds another layer of complexity to 3I Atlas's behavior. The solar wind, charged particles streaming outward from the Sun, interacts with the ionized gases in the comet's coma to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, create visible glows in the coma, and influence the development of plasma tails that extend millions of kilometers behind the nucleus. Temperature measurements during perihelion, if obtainable through spacecraft observations, could provide fundamental insights into 3I Atlas's thermal properties and internal structure. Different volatile compounds sublimate at specific temperatures, creating a chemical thermometer that reveals the heating progression within the nucleus as solar radiation penetrates its surface layers. The aftermath of perihelion will depend critically on how much volatile material 3I Atlas contains and how efficiently that material can escape through the nuclear surface. Objects with large volatile reserves might continue showing enhanced activity for weeks or months after perihelion, while those with limited volatile content could fade rapidly as their surface layers become depleted. Gravitational perturbations from the Sun's intense gravitational field near perihelion could also affect 3I Atlas's future trajectory. While the comet will definitely continue outward on its hyperbolic path, small changes in velocity could alter the timing and geometry of future encounters with outer solar system planets, particularly Jupiter in 2026. The perihelion passage represents the climax of 3I Atlas's solar system encounter, the moment when billions of years of interstellar evolution meet the intense radiation environment surrounding our star. Whether this meeting produces spectacular displays of cosmic pyrotechnics or quiet structural transformations hidden within an expanding coma, the perihelion will fundamentally alter 3I Atlas from the object that entered our solar system into something new and unprecedented. The question that will haunt astronomers through the conjunction period is whether 3I Atlas will emerge from its hidden perihelion passage recognizable as the same object that captivated observers in September, or as something entirely transformed by its encounter with our Sun's most intense radiation. The answer lies hidden in solar glare, awaiting the patient geometry of orbital mechanics to reveal what perihelion has wrought. To understand the significance of 3I Atlas and its bizarre behavior, we must look backward through the brief but revolutionary history of confirmed interstellar visitors. Only 2 objects before our current visitor have been definitively identified as originating beyond our solar system, and each has rewritten astronomical textbooks in its own unique way. The story they tell together is one of cosmic diversity that challenges every assumption about how these wandering messengers from other star systems should behave. 1I/Oumuamua arrived first, discovered on October 19, 2017, by the Panoramic Survey Telescope and Rapid Response System, PANSTARRS, in Hawaii. Initially classified as an asteroid due to its lack of a visible coma, Oumuamua quickly proved that interstellar objects would not conform to Earth-based expectations. Its highly elongated shape, roughly 400 meters long and 40 meters wide, resembled no asteroid or comet previously observed in our solar system. More puzzling still, Oumuamua exhibited non-gravitational acceleration as it moved away from the Sun, speeding up in ways that couldn't be explained by gravitational forces alone. This mysterious acceleration sparked debates that continue today. Was it outgassing from hidden volatile deposits, solar radiation pressure acting on an unusually shaped object, or something more exotic that pushed the boundaries of conventional physics? The absence of a detectable coma around Oumuamua contradicted expectations for objects containing the volatile ices typical of comets. Yet something was clearly acting on the object to produce the observed acceleration. The resolution, if it can be called that, involved invoking outgassing so minimal that it remained below detection thresholds while still generating enough force to alter Oumuamua's trajectory. 2I/Borisov, discovered on August 30, 2019, by amateur astronomer Gennady Borisov in Crimea, presented a completely different personality. Unlike its predecessor's enigmatic behavior, Borisov appeared refreshingly normal at first glance, a classic comet complete with a fuzzy coma and developing tail structures that matched theoretical expectations for objects heated by solar radiation. However, detailed analysis revealed that Borisov's apparent normalcy masked chemical compositions unlike anything found in native solar system comets. Spectroscopic observations showed carbon monoxide concentrations significantly higher than those typical of local comets, suggesting formation conditions in a protoplanetary disk with different temperature and chemical gradients than our own solar nebula. The dust-to-gas ratio in Borisov's coma also differed from solar system norms, indicating either different formation processes or evolutionary changes that occurred during its interstellar journey. These subtle but significant chemical differences provided the first direct evidence that other star systems produce comets with compositions reflecting their unique formation environments. Now, 3I Atlas enters this exclusive club with characteristics that make both of its predecessors seem mundane by comparison. The carbon dioxide-rich coma detected by SphereX and confirmed through follow-up observations represents the most extreme compositional departure from solar system norms yet observed in an interstellar visitor. The CO2-to-water vapor ratio suggested by James Webb Space Telescope analysis indicates formation conditions even more exotic than those that produced Borisov. The sunward-pointing anti-tail structure of 3I Atlas has no parallel in previous interstellar object observations. While Oumuamua showed no tail structures due to its apparent lack of significant outgassing, and Borisov displayed conventional comet tails streaming away from the Sun, 3I Atlas creates a geometry that defies basic principles of comet physics as understood through centuries of observation. The rapid brightening trend, documented in September 2025, adds another unique characteristic to 3I Atlas's growing list of anomalies. Neither Oumuamua nor Borisov exhibited such dramatic short-term brightness variations, suggesting that 3I Atlas undergoes processes, whether outgassing events, structural changes, or surface evolution, operating on timescales faster than those typical of previously studied interstellar objects. Size comparisons reveal interesting patterns in the interstellar visitor population. Oumuamua's dimensions, estimated at roughly 400 by 40 by 40 m, were significantly larger than typical small asteroids but smaller than most active comet nuclei. Borisov's nucleus diameter, estimated at approximately 1 kilometer, fell within the normal range for solar system comets. 3I Atlas presents size estimation challenges that reflect the uncertainty surrounding its fundamental nature. Hubble Space Telescope observations suggest a nucleus diameter somewhere between 0.32 and 5.6 kilometers, a range that encompasses both small and moderately large comet nuclei. The uncertainty arises from difficulties in separating the nucleus from its extensive coma, itself a unique characteristic that distinguishes 3I Atlas from its interstellar predecessors. Chemical analysis capabilities have evolved significantly between the discovery of each interstellar visitor, allowing progressively more detailed composition studies. Oumuamua's brief visibility period and lack of significant outgassing limited chemical analysis to surface reflection properties and rough density estimates. Borisov's more conventional comet behavior enabled spectroscopic detection of water vapor, carbon monoxide, and various other molecular species typical of comet comas. 3. Atlas benefits from the most advanced observational capabilities yet applied to an interstellar object. James Webb Space Telescope's infrared spectroscopy, Hubble's high-resolution imaging, and ground-based observatories equipped with next-generation spectrographs provide unprecedented detail about chemical composition, physical structure, and temporal evolution. The orbital characteristics of each interstellar visitor also tell their own stories about galactic dynamics and the processes that eject objects from their birth star systems. Oumuamua approached the solar system from the direction of the star Vega, though its journey time exceeded Vega's age, indicating a more complex galactic trajectory. Its hyperbolic excess velocity, the speed it would retain after escaping solar gravitational influence, measured approximately 26 kilometers per second. Borisov's trajectory suggested an origin from a region of space containing young, hot stars in the constellation Cassiopeia, with a hyperbolic excess velocity of approximately 32 kilometers per second. The higher velocity indicated either ejection from a more massive star system or acceleration through gravitational interactions during its interstellar journey. 3I Atlas carries the highest hyperbolic excess velocity yet measured for an interstellar object, estimated at approximately 39 kilometers per second. This extreme velocity suggests either formation around a particularly massive star or acceleration through multiple gravitational encounters during its journey through the galaxy. The velocity also influences the object's behavior near perihelion, as higher speeds reduce the time available for solar heating to penetrate deep into the nucleus interior. The discovery intervals between interstellar visitors provide insights into their population in the galaxy. The 2-year gap between Oumuamua and Borisov, followed by the 6-year interval before 3I Atlas, suggests that such objects pass through the inner solar system regularly but remain difficult to detect due to their small sizes and brief visibility periods. Statistical analysis of the 3 confirmed interstellar objects indicates that each represents a different type of small body formation process, suggesting enormous diversity in how other star systems produce and eject comets and asteroids rather than converging toward typical characteristics. Each new interstellar visitor has expanded the range of possible behaviors and compositions. The unique characteristics of 3I Atlas, the unprecedented coma size, anti-tail structure, chemical composition, and brightness evolution, suggest that interstellar object diversity encompasses phenomena not yet imagined by theoretical models based on solar system experience. Each visitor teaches new lessons about planetary formation processes throughout the galaxy while simultaneously raising new questions about what other types of interstellar objects await discovery. As 3I Atlas continues its hidden passage through perihelion, astronomers can only speculate about whether its post-conjunction appearance will add new entries to the growing catalogue of interstellar object peculiarities. The pattern established by Oumuamua and Borisov suggests that 3I Atlas will continue surprising researchers with behaviors that challenge fundamental assumptions about small body physics. The lesson emerging from all 3 interstellar visitors is that the galaxy produces small bodies through processes far more diverse and complex than those operating in our local solar system. Each object carries chemical and physical signatures of formation environments that differ dramatically from our own cosmic neighborhood, providing direct samples of planetary system evolution occurring throughout the Milky Way. The scientific community's response to 3I Atlas resembles a detective story where crucial evidence remains locked away, forcing researchers to construct theories from incomplete clues, while the most important information lies hidden behind solar glare. Multiple competing hypotheses attempt to explain the comet's unusual behavior, but each explanation raises new questions that may remain unanswered until, or unless, post-conjunction observations provide the missing pieces of this interstellar puzzle. The nucleus size and shape controversy illustrates the fundamental challenges facing 3I Atlas researchers. Hubble Space Telescope observations have narrowed the size estimate to somewhere between 0.32 and 5.6 kilometers in diameter, but this broad range reflects the difficulty of separating the solid nucleus from its extensive coma. The uncertainty matters because size directly affects calculations of mass, density, surface area available for outgassing, and structural stability during the intense heating of perihelion. Different measurement techniques produce conflicting results. Thermal modeling based on infrared observations suggests a smaller nucleus with high albedo, a reflective surface that efficiently scatters sunlight. Visible light analysis indicates a larger, darker nucleus that absorbs more solar radiation. The discrepancy could result from surface composition variations, measurement uncertainties, or fundamental misunderstandings about how 3I Atlas responds to solar heating. The observational gap during conjunction creates additional uncertainty about which theoretical models best explain 3I Atlas's behavior. The most critical tests of competing hypotheses, how the comet responds to maximum solar heating, whether fragmentation occurs, how outgassing patterns evolve, will occur largely hidden from Earth-based observation. When 3I Atlas emerges from conjunction in late November, researchers will face the challenge of interpreting observations of an object that may have changed dramatically during its invisible perihelion passage. The post-conjunction appearance could either validate current theoretical models or introduce new puzzles that require entirely different explanations. The scientific debates surrounding 3I Atlas reflect the broader challenge of understanding phenomena that occur only rarely and under conditions that push observational capabilities to their limits. Each measurement carries uncertainties, each model makes assumptions, and each interpretation must account for the possibility that interstellar objects operate according to physical principles not yet discovered through solar system experience. Before venturing into the realm of truly speculative possibilities, science demands that we exhaust the exotic but still plausible natural explanations for 3I Atlas's bewildering behavior. The comet may be strange beyond current understanding, but it likely remains within the boundaries of known physics, albeit operating under conditions so extreme that they've never been observed before in human experience. The carbon dioxide dominance detected in 3I Atlas's coma provides the first clue to understanding its alien nature through conventional cometary science. This composition suggests formation in a region of its birth star system where temperatures remained low enough for CO2 to condense into solid ice while water existed primarily as vapor. Such conditions typically occur beyond what astronomers call the carbon dioxide snowline, the distance from a star where carbon dioxide can freeze out of the gaseous phase. In our solar system, the CO2 snowline lies much farther from the Sun than the regions where most comets form. This explains why solar system comets show water as their primary volatile component, with carbon dioxide playing only a secondary role. However, other star systems could have different temperature profiles, stellar luminosities, or chemical compositions that place the CO2 snowline at distances where significant comet formation occurs. A star cooler than our Sun would push the carbon dioxide snowline closer to the star, allowing CO2-rich comets to form in the same orbital regions where water-dominated objects condense in our system. Alternatively, a star with a different chemical composition, perhaps enriched in carbon relative to oxygen, could produce protoplanetary disks where carbon dioxide formation is favored over water ice formation, regardless of temperature. The formation environment hypothesis explains not only 3I Atlas's unusual chemistry but also its enhanced outgassing behavior. Carbon dioxide sublimes more readily than water ice at the same temperature, potentially producing gas release rates that exceed those of water-dominated comets by significant factors. This enhanced volatility could account for the rapid brightening observed in September and the unprecedented size of the coma detected by SphereX. However, the CO2-rich composition alone cannot explain the sunward-pointing anti-tail that has puzzled observers since the first detailed images appeared. This is where dusty plasma physics enters the equation, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes gases in a comet's coma, it creates a plasma, a soup of electrically charged particles that responds to both gravitational forces and electromagnetic fields. This ionized material interacts with charged dust grains in complex ways that can produce self-organizing structures unlike anything predicted by simple gravitational and radiation pressure models. Charged dust particles can form streams, filaments, and even spiral structures when influenced by magnetic fields carried in the solar wind. Under specific conditions, these electromagnetic effects might overcome radiation pressure, allowing material to flow in directions that appear to violate basic comet physics. The result could be anti-tail structures that point toward the Sun while conventional tails stream away from it. The plasma physics explanation gains credibility when considering 3I Atlas's enhanced outgassing rates. Higher gas densities create more opportunities for ionization and charge exchange processes that could amplify electromagnetic effects. The unusual chemical composition might also influence plasma formation through molecular species that ionize more readily or at different rates than those typical of solar system comets. Rotation state offers another avenue for explaining 3I Atlas's anomalous behavior through conventional physics applied to extreme conditions. A nucleus with very slow rotation could develop temperature differences between its day and night sides that concentrate outgassing in specific regions rather than distributing it uniformly across the surface. If 3I Atlas rotates slowly enough that its day side reaches significantly higher temperatures than solar system comets experience, thermal expansion and gas pressure could create jets of material ejected with velocities high enough to overcome solar radiation pressure in the sunward direction. The result would be preferential ejection toward the Sun from the hottest regions of the nuclear surface. The slow rotation hypothesis requires explaining why 3I Atlas would rotate differently from typical comets. Interstellar objects experience different evolutionary processes during their journeys between star systems. Collisions with interstellar dust particles, gravitational torques from passing stars, or magnetic field interactions could all alter rotation states in ways that don't occur for objects remaining within single stellar systems. The green coloration that appeared in September presents its own natural explanation challenges. Diatomic carbon typically produces green emission in comet comas, but initial spectroscopic observations showed relatively little evidence for carbon-bearing molecules other than carbon dioxide. However, the threshold hypothesis suggests that C2 release became significant only when 3I Atlas crossed a specific temperature or solar radiation threshold near the 2 astronomical unit distance. This threshold effect could result from carbon dioxide photodissociation, the breakdown of CO2 molecules by solar ultraviolet radiation into carbon monoxide and atomic oxygen. Further photodissociation of carbon monoxide could produce the carbon atoms necessary for diatomic carbon formation. The process requires specific radiation conditions and molecular densities that might not have been present during 3I Atlas's initial observations but developed as the comet approached closer to the Sun. Alternative carbon chemistry involves complex organic molecules that could exist in trace quantities within the nucleus but produce detectable emission only under specific excitation conditions. Polycyclic aromatic hydrocarbons, amino acids, or other organic compounds could break down under intense solar radiation to produce carbon-bearing fragments that fluoresce at green wavelengths. Surface composition variations offer another natural explanation for 3I Atlas's unusual behavior. Rather than a uniform nucleus composition, the object might contain discrete regions with different chemical makeups, some rich in carbon dioxide, others containing water ice, and still others harboring complex organic materials. As 3I Atlas approaches the Sun and different regions of its surface experience heating for the first time, these chemical variations could produce outgassing patterns that change over time. The initial CO2 dominance might reflect early activation of the most volatile surface deposits, while later heating could expose subsurface materials with different compositions. Porosity and internal structure also influence comet behavior in ways that could explain 3I Atlas's anomalous characteristics. A highly porous nucleus, essentially a loose collection of ice and dust held together by weak forces, could allow deep penetration of solar heating that activates subsurface volatile deposits normally insulated from external temperature changes. The enhanced porosity hypothesis explains both the extensive coma and the rapid brightness changes. Deeper heating activates larger volumes of volatile material than typically occurs in more compact comet nuclei, creating gas production rates that exceed model predictions based on surface heating alone. Interstellar processing during 3I Atlas's journey between star systems might have created structural modifications not experienced by solar system objects. Cosmic ray bombardment, interstellar dust impacts, or thermal cycling during passages through different radiation environments could all alter nucleus properties in ways that influence behavior when the object finally encounters intense stellar radiation. The most likely explanation for 3I Atlas's extraordinary behavior involves combinations of these natural processes operating simultaneously. CO2-rich composition drives enhanced outgassing, plasma physics creates anti-tail structures, slow rotation concentrates activity in specific regions, and complex chemistry produces the observed color changes. While each individual process remains within well-understood physics, Their interaction under the extreme conditions of an interstellar comet encounter might produce phenomena that appear impossible when considered through the lens of solar system comet experience. 3I Atlas could represent a profoundly weird comet rather than something fundamentally alien, but that weirdness makes it precisely the type of object that could revolutionize our understanding of small-body physics throughout the galaxy. Now we venture into territory where science fiction meets speculative possibility, where the boundaries between natural phenomena and truly extraordinary explanations begin to blur. While no credible evidence supports these exotic interpretations of 3I Atlas's behavior, the comet's unprecedented characteristics invite the kind of speculation that has accompanied every unexplained astronomical phenomenon throughout human history. These ideas exist not as serious scientific hypotheses but as thought experiments that illuminate just how strange our interstellar visitor truly is. The alien technology beacon hypothesis represents perhaps the most persistent exotic explanation for unusual astronomical objects. Ever since 1I/Oumuamua's discovery sparked debates about artificial origins, each new interstellar visitor inevitably generates speculation about possible technological signatures. 3I Atlas's rapid brightening, unusual anti-tail structure, and enhanced coma could theoretically represent activation sequences of some form of automated probe designed to respond to stellar radiation environments. The beacon scenario imagines 3I Atlas as a dormant technological artifact that remained inactive during its long journey between star systems, preserving power and structural integrity until encountering conditions that trigger preset activation protocols. The brightening event in September could mark the moment when solar radiation reached sufficient intensity to power dormant systems, while the anti-tail structure might represent directed energy emissions or material ejections serving some technological purpose. However, this technological interpretation faces immediate challenges when confronted with observational evidence. The spectroscopic signatures detected by the James Webb Space Telescope and ground-based observatories show clear evidence for standard volatile compounds, carbon dioxide, water vapor, and organic molecules, that match expectations for natural comet outgassing. No unusual isotopic ratios, artificial materials, or energy signatures characteristic of advanced technology have been detected. The quasi-living plasma hypothesis ventures even further into speculative territory, drawing on research into complex plasma behaviors that can exhibit seemingly organized patterns under specific conditions. Laboratory experiments have demonstrated that dusty plasmas, mixtures of charged particles and microscopic solid grains, can self-organize into structures that exhibit properties reminiscent of biological systems. These plasma formations can reproduce, evolve, and respond to environmental changes in ways that superficially resemble living organisms. Some researchers have speculated that such complex plasma systems might arise naturally in space environments, potentially developing behaviors that mimic primitive life forms. 3I Atlas's unusual outgassing patterns, anti-tail structures, and responsive brightening could theoretically represent manifestations of such plasma-based phenomena. The living plasma concept suggests that interstellar space might harbor forms of organization that operate according to physical principles completely different from carbon-based biology. These hypothetical entities might remain dormant during interstellar travel but become active when encountering the electromagnetic environment surrounding stars, producing observable effects that mimic but don't truly represent biological processes. Yet, this explanation requires invoking physical mechanisms that remain purely theoretical. While dusty plasmas can indeed form complex structures under laboratory conditions, scaling these phenomena to comet-sized objects operating in the solar wind environment requires extrapolations far beyond current scientific understanding. No observational evidence suggests that 3I Atlas exhibits the type of electromagnetic signatures expected from large-scale plasma organization. The purposeful scout narrative transforms 3I Atlas into an active reconnaissance mission from another star system, complete with programmed behaviors designed to study our solar system during its passage through the inner regions. This scenario imagines the comet's unusual characteristics as intentional features. The extensive coma might provide sensor capability or communication range, while the anti-tail structure could represent data transmission systems aimed at distant receivers. The Scout hypothesis suggests that 3I Atlas's brightening represents not random outgassing but controlled activation of observation and communication systems as the object approaches its primary mission targets. The timing of peak activity, near Mars and during perihelion, could reflect predetermined survey protocols rather than simple responses to solar heating. This interpretation leads to romantic speculation about 3I Atlas waking up as it encounters the radiation signature of our star system, its artificial consciousness stirring after millions of years of dormant interstellar travel. The green coloration might mark the moment when dormant sensors begin functioning, while the rapid brightness changes could indicate data processing and transmission activities. However, the Scout scenario faces the same evidentiary challenges as the technological beacon hypothesis. The chemical signatures, thermal behavior, and structural characteristics of 3I Atlas all match expectations for natural objects, albeit unusual ones. No evidence suggests information processing, directed communications, or other activities characteristic of technological systems. The exotic matter hypothesis proposes that 3I Atlas contains materials or operates according to physical principles unknown to current science. Theoretical physics suggests possibilities for exotic forms of matter with unusual properties, dark matter interactions, modified gravitational behaviors, or quantum effects operating on macroscopic scales that could produce observable phenomena unlike anything in standard physics. Exotic matter could potentially explain 3I Atlas's unusual anti-tail through gravitational anomalies that redirect material flow, or account for its enhanced outgassing through energy release mechanisms beyond conventional chemistry. The rapid brightening might reflect exotic phase transitions or energy storage systems that operate according to physics yet to be discovered. This explanation allows for natural phenomena that nonetheless transcend current scientific understanding, suggesting that 3I Atlas represents not artificial technology but natural processes involving physics that human science hasn't yet encountered. The object could serve as an inadvertent laboratory for studying physical principles that don't manifest under conditions typical of Earth-based research. The temporal anomaly speculation ventures into the most exotic territory, suggesting that 3I Atlas might represent some form of information or matter transfer across cosmic timescales. Science fiction scenarios imagine the comet as a message or artifact from our own future, sent backward through time using technologies that circumvent conventional causality constraints. This interpretation treats 3I Atlas's unusual properties as evidence for temporal manipulation rather than spatial travel between star systems. The object might originate from a future version of our own solar system, carrying information or materials intended for our current epoch. Its strange behavior could reflect interactions between future technology and present-day physical conditions. However, temporal manipulation scenarios require physics that not only remains unproven but contradicts fundamental principles of causality and thermodynamics as currently understood. No observational evidence suggests that 3I Atlas violates conservation laws or exhibits temporal anomalies beyond the normal relativistic effects expected for high-velocity objects. A critical perspective on all these exotic explanations emphasizes how often apparently mysterious astronomical phenomena receive mundane explanations once sufficient data becomes available. Pulsar discoveries initially generated speculation about artificial signals from advanced civilizations, but these objects proved to be rapidly rotating neutron stars. Fast radio bursts sparked similar debates before being traced to natural astrophysical processes. History suggests that 3I Atlas will ultimately find explanation within known physics, albeit perhaps involving processes or conditions not previously observed. The comet's unusual characteristics likely reflect the extreme diversity of conditions present in other star systems rather than manifestations of exotic physics or artificial technology. The value of exploring these speculative scenarios lies not in their probability but in their ability to highlight just how extraordinary 3I Atlas truly is within the context of human astronomical experience. An object that can seriously inspire considerations of alien technology, living plasma, and exotic matter represents something genuinely unprecedented in our understanding of interstellar visitors. As 3I Atlas continues its hidden passage through perihelion, these exotic explanations serve as reminders of how much we still don't understand about the universe beyond our solar system. Whether the comet emerges from conjunction as a thoroughly mundane, if unusual, object, or continues displaying characteristics that challenge conventional explanations, it has already succeeded in expanding the boundaries of what we consider possible for visitors from other star systems. The cosmic clock ticks toward a series of moments that will determine not only what 3I Atlas reveals about itself, but what it teaches us about the broader population of objects wandering between the stars. Each upcoming milestone represents a crucial test of our understanding, our observational capabilities, and our ability to extract meaningful science from phenomena that push every limit of current astronomical practice. October 3, 2025 marks the first critical juncture. 3I Atlas's closest approach to Mars at approximately 30 million kilometers. This encounter represents humanity's best opportunity to maintain surveillance of the interstellar visitor during the period when Earth-based telescopes begin losing sight of it. The mechanical eyes orbiting Mars will attempt observations never intended by their original mission designs, stretching technological capabilities to capture images and spectra of an object racing past at interstellar velocities. Success depends on variables beyond human control. If 3I Atlas maintains or enhances its current brightness levels, the Mars orbiters might capture detailed images of nuclear structure and chromodynamics invisible from Earth. However, if the comet fades from its September peak, even the most sensitive spacecraft instruments might detect only marginal signals insufficient for meaningful scientific analysis. Late October brings the hidden climax. Perihelion on October 29 to 30 at approximately 1.36 astronomical units from the Sun. During these critical days, 3I Atlas will experience radiation intensities that could trigger the most dramatic transformations of its entire solar system encounter. Maximum heating might activate volatile compounds that have remained stable throughout the comet's interstellar journey, potentially creating outgassing events spectacular enough to alter the object's fundamental characteristics. Yet, perihelion occurs almost exactly when 3I Atlas becomes most difficult to observe from Earth, hidden in solar glare that no ground-based telescope can penetrate. The cosmic irony places the moment of maximum scientific interest precisely when human observational capabilities reach their minimum effectiveness. Whatever revelations perihelion produces will remain largely hidden from direct observation, preserved only in whatever indirect evidence survives for later analysis. The observational gap extends through early November, creating a 4 to 5 week period when 3I Atlas effectively vanishes from human monitoring. This forced silence occurs during what theoretical models predict should be the comet's most active phase, potentially encompassing fragmentation events, dramatic brightness changes, or chemical transformations that would normally generate intensive observational campaigns. Re-emergence in early December represents the next critical milestone, when solar elongation increases sufficiently for Earth-based telescopes to relocate and track 3I Atlas after its hidden passage. The comet that emerges from conjunction might bear little resemblance to the object that disappeared in October, potentially showing signs of fragmentation, dramatically altered brightness, or evolved chemical composition reflecting its encounter with intense solar heating. The post-perihelion timeline extends the scientific opportunities through the following year and beyond. A Jupiter approach in March 2026, while occurring at a much greater distance than the Mars encounter, might provide additional spacecraft observation opportunities as 3I Atlas begins its final exit from our solar system. The geometry could allow distant observations by missions like Juno or the forthcoming Europa Clipper, depending on their operational status and orbital configurations. What we could learn from successful observations extends far beyond the specific characteristics of 3I Atlas itself. Interstellar chemistry analysis provides direct samples of materials formed around other stars, preserving information about chemical conditions present in protoplanetary disks throughout the galaxy. The carbon dioxide-rich composition already detected hints at formation environments unlike our local solar nebula, suggesting that planetary system chemistry varies more widely than previously imagined. Comet behavior studies under extreme conditions could revolutionize our understanding of volatile release mechanisms, dust grain dynamics, and plasma physics in extraterrestrial environments. The anti-tail phenomenon challenges fundamental assumptions about how comet materials respond to solar radiation, potentially requiring new theoretical frameworks that account for electromagnetic effects not considered in conventional models. The scientific implications extend to broader questions about interstellar objects and their role in chemical evolution throughout the galaxy. 3I Atlas represents only the third confirmed visitor from another star system, but its unusual characteristics suggest that the galaxy harbors far more diversity in small body formation than current theories predict. Each interstellar object studied provides crucial data points for understanding how common such visitors might be and what they reveal about conditions in distant stellar systems. Fragmentation analysis: if 3I Atlas undergoes breakup during perihelion, could provide unprecedented insights into interstellar object internal structure and composition gradients. Different fragments might contain materials from various depths within the original nucleus, effectively providing core samples of an object formed around another star. The fragment dispersal patterns and chemical differences could reveal structural details impossible to determine from intact object observations. Expectation management requires acknowledging the limitations inherent in studying objects that remain at the threshold of detectability even under optimal conditions. 3I Atlas will likely never become a naked-eye spectacle for Earth-based observers, with peak brightness estimates hovering around magnitude 11 to 12, well within telescopic range but invisible without optical aid. The lack of a dramatic visual display doesn't diminish the scientific value, but it does limit public engagement opportunities that often drive continued funding and interest in astronomical research. The European Space Agency's future Comet Interceptor mission, scheduled for launch in the late 2020s, represents one attempt to develop rapid response capabilities for studying newly discovered interstellar objects. Unlike traditional spacecraft missions that require years of planning for specific targets, Comet Interceptor will wait in space at the Earth-Sun L2 Lagrange point until a suitable target appears, then redirect to intercept and study the object during its solar system passage. However, Comet Interceptor's capabilities remain limited by the fundamental challenge of detecting interstellar objects early enough to allow spacecraft intercept missions. 3I Atlas was discovered only months before its closest approach to the Sun, providing insufficient time for dedicated spacecraft missions, even if such rapid response capabilities existed. Future detection systems must identify interstellar visitors years in advance to enable meaningful spacecraft encounters. Ground-based survey improvements offer more immediate prospects for enhancing interstellar object science. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s with unprecedented sky survey capabilities. Its ability to repeatedly image large portions of the sky could identify interstellar objects much earlier in their solar system passages, providing extended observation periods and better opportunities for detailed study. The Legacy Survey of Space and Time, Rubin Observatory's primary mission, expects to discover interstellar objects at a rate of several per year once full operations begin. This dramatic increase in detection frequency will transform interstellar object studies from rare opportunistic observations to systematic population studies that can address fundamental questions about galactic small-body reservoirs and their chemical evolution. Technological developments in adaptive optics, spectroscopy, and space-based observations continue expanding the limits of what can be learned from faint, rapidly moving targets like 3I Atlas. Next-generation extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, will provide light-gathering power and spatial resolution that could revolutionize interstellar object characterization. The James Webb Space Telescope's infrared capabilities have already demonstrated their value for interstellar object studies, providing chemical composition data impossible to obtain with previous instrumentation. Future space-based observatories optimized for small-body studies could provide continuous monitoring capabilities unaffected by Earth's atmospheric limitations or solar conjunction periods. International cooperation becomes increasingly crucial as interstellar object studies require coordinated observations across multiple facilities and time zones. The 3I Atlas Observing Campaign has demonstrated both the potential and the challenges of organizing a global response to rapidly evolving astronomical targets. Lessons learned from this coordination effort will inform future responses to similar discoveries. Data sharing and analysis protocols developed for 3I Atlas observations are establishing standards for how the astronomical community handles rapidly changing, high-priority targets that require immediate response from multiple observational facilities. These protocols will prove essential as interstellar object discovery rates increase and opportunities for coordinated study become more frequent. The broader implications extend beyond astronomy to fundamental questions about the nature of matter and chemistry throughout the galaxy. 3I Atlas provides direct physical evidence about conditions in other star systems, preserved in pristine form during millions of years of interstellar travel. Each measurement contributes to our understanding of how planetary formation processes